All right, what we're going to be looking at is chapter 26, part 2. And we will be looking at speeds of light and sound, how they compare, the Doppler effect for light, transparent materials, and the index of refraction. So, comparing the speeds of light and sound. Well, light is much faster than sound. It's 1,000,000 times faster. So, when a lightning bolt occurs, we see the lightning because that light moves at 3 times 10 to the 8th meters per second. The sound also occurs, but that moves much more slowly. So, the light gets to our eyes first, and we see the light before our ears hear the sound. Okay, and there can be a considerable gap between the light and the sound. It depends on how far away your ear is and your eyes are from the event. And every 5 seconds that pass between seeing the lightning and hearing the sound, that gives you a distance of about 1 mile. Okay, so if it takes 10 seconds between seeing the lightning and hearing the thunder, then that would indicate that it's 2 miles away. Okay, so 5 seconds per mile. Now, how good is that? Well, let's look at the formula that we've used before. Distance is velocity times time. So if we were looking for time, that would be distance divided by velocity. So in this case, if lightning occurs 1 mile away, which is 1.609 kilometers, how long would it take for the light and the sound to reach us? Okay, so for sound, we would use the distance, 1609, divide by the velocity, 344 meters per second, and that would take nearly 5 seconds, okay, 4.68 seconds. For sound, we use the same distance, but the much higher velocity, and we would find that the time is only half of 10 to the minus fifth seconds, which is 5.4 microseconds, and micro means 1 millionth. Okay. So they're each about half of something, about 5 seconds versus 5 millionths of a second. So again, that's why it's definitely faster to see the light than to hear the sound. That will occur faster, but also you see that it is about 5 seconds for 1 mile. And so this happens with fireworks also. Same issue. You see the light of the firework, then you hear the sound later, as we played around with in the lab already. Okay, now you recall we already covered the Doppler effect for sound. Well, the Doppler effect for light also occurs, as we talked about a little bit. And the idea is that you can have a source of sound or light moving towards an observer. So if it's moving or approaching an observer, then you are going to hear a higher pitch. And you'll hear a lower pitch if it is moving away or departing. Okay, so the same thing occurs for light. And here's a nice, so this is sort of showing again the sound in front of a race car. And so as it approaches, the waves bunch up. Behind, the waves are spread out. This is showing with some water. And so, but again, for light, we call it a blue shift and a red shift. A blue shift is a shift to a shorter wavelength, which is a higher frequency. The red shift is a source, the source is moving away, and that gives you a longer wavelength. Okay, so shorter wavelength for approaching or moving toward, longer wavelength when it's moving away. And so we use this all the time in astronomy. We already talked about using it for radar, which of course is radio waves. This is how the police catch your car moving too fast. So that would be um, um, infrared or radio waves that they use. Um, and and astronomers use it to look out into space and to tell whether or not stars are moving towards us or away from us, and to see which way the sun rotates and the different speeds on the different edges. It's all amazing stuff. So anyway, so we look at atomic spectra, and for atomic spectra, this would show a spectrum at rest in this location. If it's moving towards you, all these lines move towards the blue end of the spectrum. They don't have to become blue, they just have to move towards the blue end or higher frequency, and that would be moving towards you. If it's moving away, then that shows a red shift. So all the lines in this spectrum are moving towards the red end. Okay, now some materials are transparent. How does that work? How does light just sneak through a material? Well, it turns out light doesn't just sneak through the material. It actually gets absorbed and re-emitted. And so it passes from atom to atom, but basically it gets rejected by the atom. It doesn't get absorbed permanently. So it gets absorbed and then rejected. So it makes the atom vibrate, but it doesn't vibrate at quite the right level. So then it sends it along. So remember we talked about resonance. Some materials, some light waves will resonate with the material, and then they get absorbed into it permanently. But is one way to think about it. But others will reject it. So it doesn't quite, it's not at quite the right frequency. Okay, so for transparent materials, what happens is the beam of light goes into an atom, gets absorbed, gulp, and then rejected, burped back out. And this happens over and over again through the millions and millions of atoms that might be in a pane of glass or a crystal vase. So what happens is that it keeps getting absorbed. It gets emitted as a photon of light. The photon of light you can think of as like a beam of light, but it's a packet of light. It's acting more like a particle. So this is considered a particle of light, is a photon. And so the light, of course, is slowed down as it goes through the material because it's spending all this time being absorbed and re-emitted. Okay, so what this does is it causes the materials to have different speeds of light as it passes through them. So in a vacuum, all electromagnetic waves travel at 3 times 10 to the 8th meters per second. And in the atmosphere, it's very close to that. But when you get into water, the velocity is only 0.75 or 75% of c, the speed of light. And that's only about 2.3 times 10 to the 8th. So we've made light slow down by viewing it through water. And I'm going to take, let's keep looking at this. Actually, I'll take this camera over here. You can see I've got some different materials here. So I've got a globe of water and a bin with water. So there's water here and here. So the light is passing through those at a certain speed. Then there are objects which are made of glass. And in glass, the speed is down to 0.67 or 2/3 of its normal speed. So it's down to 2 times 10 to the 8th. So like this glass box or glass sphere. If it's in a diamond, it's down to 0.41. So less than half the speed of light. So like this diamond, no, I'm joking, that's a quartz crystal. Anyway, but through quartz, it's a different speed. Yeah. I don't have a big diamond here. Okay, so what this leads to is what's called the index of refraction. Objects go at different speeds in different materials. And those can be given a number that's based on the formula. Let me change to a color. We'll actually be able to see where it's the velocity in the vacuum divided by the velocity in the material. So if we were looking at glass, then we would have 3 times 10 to the 8th meters per second divided by 2 times 10 to the 8th meters per second. And so that would be 3 over 2 would be 1.5. So the index of refraction for glass is 1.5. Putting in some of these other numbers, we've got air, of course, would just be 1. Water is 1.33. A diamond is 2.4. And I used to work with materials when I was an engineer that had index of refractions up to 4.2. So yes, so the index of refraction, the higher the number, the slower the light is going. Okay, now it's called the index of refraction because when light goes through materials and it goes from like air to glass, then what happens is that this can change its path. So that's why looking at these objects, you're seeing some squirrely looks of stuff because what's happening is that the light is going and changing its path because it's changing its speed. It's doing what's called refracting. And does that matter? Well, let's look at these globes of water here. All right, we've got a circular one here, and you can see how things are messed up. And then we've got this one, and you can see perhaps that there's a glass marble inside that one. Let's see if I can lock down the percent. There we go. Hopefully you're seeing what I'm seeing right now. Okay, so what I'm going to do is we're going to dig that marble out. So plastic, translucent spoon, right? Now when I put it in the water, you can still see it, right? Because the thing is we can see at least the edges and it bends the light a little bit more. But the thing is there are some things in here, like here's the marble, right? But the marble's still in there. Well, look. Here's another marble. Okay, why can't I see these marbles? Well, because these marbles are not made of glass. A glass marble in water I can see, but these marbles are called water marbles because they actually are soft and squishy, so they're breaking apart because they're mostly water. So what happens is the light doesn't bend as it goes from the water through the marble, so you don't see the marble till it comes out in air. Because now the light from the air to the marble is going at a different speed. So once it puts back in the water, you don't see it anymore. Whereas I can see the glass marble in the water, I can also see it in the air. Okay, so if things have the same index of refraction, then the light doesn't bend as it passes from one to the other. Okay, and as we talked about with climate change and the greenhouse effect, different materials are transparent sometimes to different wavelengths. And so we talked about how visible light can get through glass, but infrared is blocked by glass. And it turns out most ultraviolet light is blocked by glass also, which is why you can't just sit in your room and get a tan through the open window or through the glass window because the glass will block the ultraviolet that gives you your sunburn. Anyway, so yes, so some materials will be transparent to certain wavelengths and opaque to others. All right, so that's the end of this part. Oops, that's not what I meant to do. All right, so we're going to go on to part 3. And, oh, shoot. Okay, you guys weren't seeing that. um, okay, so as I was saying, ultraviolet and infrared are blocked by glass, but visible light is allowed through. Okay, and we're going on to part 3. We're going to be looking at opaque materials and shadows and eclipses.